the first step in any good word problem is to read it and make sure you can clearly identify what you know and what you don't. You might remember this process because we did it at the end of chapter 1. Do you notice a pattern here? After chapter 1, we did some word problems. After chapter 2, we do some word problems. So I teach you all the stuff, and then we use it. It's kind of the trend for the chapters that we encounter in our class. So word problems for chapter 2, quadratics. The first step in any good word problem is to, like I said, read it, and then identify what you know, and identify what you don't. We're going to do that in just a second. I'm going to give you a heads up on the types of problems in this packet. There's only 2 types, honestly, 2 types of problems. You're either throwing an object or dropping an object. Let's think about throwing an object for a second. Imagine, like, if I threw Ben across the room. I'm just kidding. Wow, violent. I don't know where that came from. Imagine I threw a baseball. It kind of follows an arc motion, right? Yeah. That arc motion has meaning in math class. It's a parabola. Have you heard that before? I think we've talked about that word, right? So parabolic motion is really common when we throw an object or when we drop an object. Keep in mind parabolas are officially defined in Algebra 2 as U-shaped graphs. But when we throw an object, it's actually an upside down U. So it is still parabolic, it's just upside down to make that arc sort of motion. So you're going to see 2 types of word problems as you work through the packet, but all of them can be modeled with parabolas. All of them are going to be quadratics. Okay, so now back to step 1. In any good word problem, we start by reading the problem and identifying what we know and what we don't. So in number 1 here, Jason jumped off a cliff into the ocean, thank heavens, in Acapulco, where he was vacationing with some friends. His height as a function of time could be modeled by the function h. That stands for height. H of t, t stands for time, equals negative 16t squared plus 16t plus 480, where t is time in seconds and h is height in feet. You see that little thing right there? Called your function. We talked a lot about those yesterday. That function is what we call a quadratic function in standard form. It is a function of the form ax squared plus bx plus c, and we can use the quadratic formula on it. For the sake of those that could not be with us yesterday, I am going to show you how to work out this problem using the quadratic formula. Is that the best technique for this problem? No. But since I missed quite a few heads yesterday, and to drive home the point that you can always use the quadratic formula as your panacea for solving a quadratic, we talked about that word yesterday, your cure-all for solving a quadratic, to show that you can always use that method, I'm going to use it here. Is it appropriate? It's not my fave for this one. I would probably factor this problem ultimately at the end. Actually, I did. When I did the problem, I factored it. All right. So I read the problem. Do you see that they kind of took care of the variables for us a little bit? So h, just to review, is height in feet, and t is time in seconds. Reading the rest of the problem, in part A, we're supposed to identify how long it took for Jason to reach his maximum height. How long, so I need a time there. If it's asking me how long, this answer is going to be t equals something. In part B, I'm supposed to figure out what his highest point was. So that's going to be a height. H equals something when I'm done. And lastly, in part C, it says Jason hit the water after how many seconds? So it's asking us, ooh, I missed. How many seconds it's going to take for him to hit the water. When I'm answering the question, how long, I'm responding to an amount of time. So I kind of figured out what I'm looking for. I'm going to figure out what, I don't know here. And I kind of did that. The next step in the problem is to write an equation. Well, that equation has been done for us. So nice. And then after we write our equation, we go ahead and we solve the equation. Like I said, I'm going to show you 2 methods for solving. The first method, because in your presentation tomorrow, you have to draw me a picture. I'm going to go ahead and show you how you could produce a picture of what's going on in this scenario. So let's do that. You're going to need your graphing calculator for this part. Because ultimately, it's not like you're going to freehand this picture of like Jason falling off a cliff. You're going to rely on your calculator to produce that image, okay? And then you're just going to kind of copy for your classmates what your calculator was showing you. So we have an equation, and we're going to graph it. The equation is negative 16t squared plus 16t plus 480. Ooh, humor me for a second. I see some of you typing in already. That's great. Humor me for 1 second. Some of you are in CHS ProbStat right now. Some of you might be in, programming and you're using your calculator for different things right now. Some of you are in chemistry and your calculator might be in a certain mode. So that we're all in the same mode, looking at the same screen at the same time, you need to do these steps with me or else your calculator might mess you up. Second, plus 7, 1, 2. This is called resetting your RAM. And you can tell it's done when it says RAM cleared. You don't always have to do this. I'm just doing this so that we're all on the same page. And this squashes a ton of questions that I typically get. Mrs. Lucas, mine doesn't look like yours. So now we're all on the same page. And so now your calculator should look like mine. All right, back to the y equals screen. We're going to go ahead and type our equation in. The equation here is negative 16t is going to be x squared plus 16t, which is going to be x, our variable in this problem, plus 480. Okay, if I press graph right now, what? That is not a parabola. Nope, no it's not. That looks like 2 vertical lines to me. So I know right off the bat that is not the image that I'm looking for. Like I said, we're looking for parabolas or U-shaped graphs. So I need to adjust something called my window. So press window for me. This is something that you're going to have to show your classmates when you do the problem. Okay? X. In the problem, we need to fix our X values. In order to fix your X values, you need to think practically about what X represents in the problem. Notice I swapped out X for T in the equation when I typed it into my y equals screen. Do you remember? We didn't type negative 16t squared. We typed in negative 16x squared. So what does X stand for in the problem? John. Time. Very good. Okay, look at that right now. I have a negative value for time as my X min. What do you think about that? I have a negative X value right now. So I'm plotting negative time. What do you think about that? Go ahead, Helene. Yeah, you can't go back in time. It'd be nice, but we can't. So, Helene, how would you maybe adjust this minimum X value? Thinking again practically about the situation. This guy's jumping off a cliff, right? Into an ocean. What are some possible intervals of time that we might want to consider for the problem then? Do you want to start counting at 10 seconds? Yeah, start counting at 0. And then where do we want to stop counting? Seconds. How long do you think it's going to take him to fall in? Is it going to be minutes? Do I need like 60 seconds or 120 seconds? Is he going to fall for minutes? I need an estimation. What do you think, Tammy? You think he's going to fall for minutes? Like 60 seconds. Let's roll with it. I'd probably scale that a little bit differently. Did you know that XSCL stands for scale? Did you guys know that? Ben? Yeah. Okay. So if I'm going from 0 to 60, probably ticking off by ones, meh, not so great. Maybe go by tens. So what does y stand for in this case? Notice we did swap out y. It was a little more subtle. Height. Do I need negative height? No. So what are you going to start at? Yeah, that's probably good. To get the y maximum, I use the numbers in the equation. Do you see how the number 480 was in the equation? That's usually our y-intercept. If you let t equal 0, that's going to be the place where the graph crosses the y-axis. So I use the numbers in the problem to help me establish my y-min and my y-max. So if it has 480 in the equation, what's a good y-maximum? What do you think, John? 500. I think that's great. And I'd probably scale it by, I don't know, what, 50s? You can go by 50s, you could go by 100. And now I'm going to press graph, and I'm going to see if it took them a minute. Whoa. Nope. So this was, we went 60 seconds, right? 10, 20, 30, 40, 50, 60. It's less than 10 seconds. So I'm going to adjust this a little bit so I can see that. Maybe we'll go from like 0 to 10, do you think, to kind of see this a little bit more? You follow what I'm saying, Tammy? Okay. So maybe 0 to 10 seconds, go by ones. That's a little better. See, I can actually like visualize him. Like this would be the path that he kind of follows. Do you see that? When I look at the parabola, it should kind of depict the scenario. Now, when you go to make this picture for your classmates, like you could get as creative as you want, or you could just draw this. Like you could draw him standing there and like, oh, or you know, however you want to do it. Some people get really, really creative with it. But I just want a mathematically accurate picture. So to me, how you scale things is more important than necessarily like, oh, you have like a stop action, like guy, like picture of a guy like falling. That's what I'm going after anyways. So I'm going to steal this, and you're just going to draw it. And you're going to just kind of draw it off to the side. When you draw your diagram, you know, it's real common that we label it. So this was our h-axis. This was our t-axis. You know, you put 0 on your graph, and we scaled this by ones. And we took it all the way out to 10 seconds. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we went all the way up to 500 feet, and we scaled that by 50s. You don't always have to label every tick mark. You can if you like, but really it's the first tick mark you have to have labeled. And this is Jason. That point right there is the point 0, 480. This is what we call the y-intercept, if you'll recall from chapter 1. It's found by letting x, or in this case t, equal 0. So if you subbed in 0 into this problem, you'd get 480. That tells me some information. It actually helps me answer some of the questions that are now in part A and part B. Remember, you don't write it down if you don't understand it. So right now you're drawing and labeling a picture of Jason and his path that he takes from the cliff to the ocean. Does anybody have any questions on why I have that 0, 480 there, or why it's the t-axis and not the x-axis, anything like that? No? All right, good. So let's see how this picture could help us answer our questions. In part A, it says, how long did it take for Jason to reach his maximum height? Well, look at it. How high up is he at his highest point? It's actually on that picture right there. Do you see it? Come on, Alexis. Yeah. Jason reached his height. His max height. At t equals 0 seconds. Part B. What is his highest point? Go ahead, John. Yeah. The highest point Jason reached was 480 feet. That was actually his initial height, where he started from. That makes sense, people, because he's jumping and falling into the ocean. His max height has to be his initial height. Part C. Jason hit the water after how many seconds? So look at that graph. The graph supports our answer, but ultimately what you're going to do is you're going to use one of the methods, algebraic methods that we talked about in the chapter, to support why the answer exists where it does on the graph. But you could look at the graph to get a general idea of where your answer should be. So my question to you, my very smart period 6 college algebra class, is how many seconds did it take for Jason to hit the water? You see it? Go ahead, John. 6 seconds, very good. So Jason hit the water after 6 seconds. Now, it's nice that our picture does support this response, but ultimately your test is going to rely a lot on the method that you use, algebraic method you use to support your answer. So please understand that though there's an answer on our picture, you have to either use factoring, the quadratic formula, completing the square, or the square root method to support your response. This is something you're going to have to do for your classmates tomorrow. Tomorrow, you get to pick whatever method you want to do this step. Because there were quite a few of you out yesterday, I'm just going to use the method that we talked about yesterday. I'm going to show you the quadratic formula. Is that the best method for this problem? No. I would factor this problem if it were me. But the quadratic formula will produce an answer for you every single time. And because, again, some of you weren't here yesterday, here's your example. You ready? You're going to ultimately go home and watch the video, fill in the notes if you haven't done so already. But here is another example for you to go off of. So it says, Jason hit the water after how many seconds? What they're saying there is if he hit the water, that height there, h of t, is going to be 0. So ultimately, we have to let our final height in the problem equal 0. Does that make sense? Why that is? We have to let our final height equal 0 because that's the height at the ground. It's called ground zero sometimes, you know. It's because height is 0 there. So in my equation that I highlighted up here in yellow, this guy here, see, remember him? I highlighted him. That equation, I'm going to sub in 0 for h of t. And then we're going to solve this problem using the quadratic formula. We can solve for t now. A is your coefficient of your x squared. B is your coefficient of your x. And C is your coefficient, I'm sorry, I misspoke. C is your constant tagged on at the end. Remember, these are your notes. What goes on the smartboard does go in your notes. So we're going to do x equals negative b plus or minus square root b squared minus 4ac all over 2a. That's the quadratic formula song. So you can remember it. And then for those of you that were here yesterday, you remember I usually break this guy down into 3 chunks when I work these problems out. So I simplify, if I can, negative 16. I can't, so that stays. I also then usually chicken out and go to the bottom. I'm going to simplify 2 times negative 16. That's negative 32. 16 squared is 256. Minus, and then I have to do 4 times 480 times negative 16, or 4 times negative 16 times 480. I don't do anything fancy with the signs here because I brought my minus across. So right now in my calculator, I just found the product of 4 times negative 16 times 480. So when I multiplied those three things together, I did get negative 30,720. Minus a minus makes a plus. So to simplify that radicand, in other words, to simplify that number underneath the radical, I'm just going to go ahead and add 256 to it. And you get 30,976 all over negative 32. You actually can take the square root of 30,976. It's 176. And I can actually simplify this. Remember, you get two answers. I'm going to do negative 16 plus 176 over negative 32. And then I'm going to evaluate negative 16 minus 176 over negative 32. Eyes on the prize. What am I trying to get to? We said that the answer to our problem is right there. I'm algebraically supporting right now why it takes him 6 seconds to hit the ocean. Do you see how he hit the ocean at 6? He's happy. He made it to the water safely. So here's how the algebra sort of pushes that answer out. If I did negative 16 plus 176, divided that by 32, you get negative 5. But Helene said it. We can't have negative time, right? So this answer is garbage. But if we do negative 16 minus 176, divide that by negative 32, you actually do get an answer of 6. So that's how the algebra supports what our calculator produced graphically. It's pretty cool, I think. I like it when the numbers all make sense like that. What's up, John? Right. Do you see how one doesn't work? Yeah. Parabolas quite commonly can have two intercepts because they're U-shaped graphs. They could hit the graph twice. They could also hit it once, or they could hit it not at all, depending on where the U is. That kind of goes back to that, fundamental theorem of algebra where, like you look at the degree of the problem, and that tells you how many solutions you can have at most. So we can have two solutions, one solution, or no solutions. This one would have two, but one of them is kind of extraneous for the situation. Does that help you out? That's not you. Okay. So does anybody have any questions about how I did this one? So this is a process you're going to replicate tomorrow, like when you make your poster, and then present to the class. I'm going to do one more just to make sure you understand the expectation that you have to meet when you come back to class tomorrow. Number 2, if a toy rocket is launched vertically upward from ground level with an initial velocity of 128 feet per second, then its height h after t seconds is given by the equation h of t equals negative 16 t squared plus 128t. If air resistance is neglected, so there's no coefficient of friction for this problem. Now what we're going to go ahead and do is, kind of read through the rest, but we're going to produce a picture, a graph in our calculator, and it says how long is it going to take for the rocket to return to the ground. It says after how many seconds will the rocket be at 112 feet above the ground? How long will it take for the rocket to hit its maximum height? And what is the maximum height of this rocket? So the first thing I kind of do is I read through the problem. They told me what I know and what I don't. I don't know h and I don't know t. Those values are going to vary. In part A, however, it says how long is it going to take for the rocket to return to the ground? Remember, whenever you see the word ground, you want to think, hey, let h of t equal 0. we need to figure that out. Remember I said that you're always going to produce some sort of image of the problem for me. That always comes from graphing your quadratic in your y equals screen. So we're going to go ahead and type our equation into y1 there. So this equation was, where did I put my paper? There it is. You had negative 16t squared plus 128t. And then no 480, so we gotta get rid of that. Press crack. Hey, look at that. That actually worked out. Pretty nice. I don't know that you need all these y values up high. You know, so I can get rid of some of those high up y values, you know, maybe take our y max down to like 300 just to get a more accurate depiction. Kind of what we're looking at there if you launch the rocket. I am going to go ahead and take a moment now to draw this picture. You want to always draw your pictures when you go to, you know, talk about them. So I'm going to go ahead and steal this, and you can just jot it down in your notes. There's my picture there. It says, how long will it take for the rocket to return to the ground? Well, I see that, remember, this is your t-axis or your time. This is your h-axis or your height. We went from 0 seconds to 10 seconds. We scaled it by ones. We went from 0 feet to 300 feet on the y-axis there, and we went by 50s. So you could look at the picture and figure out how long it took for the rocket to hit the ground. Do you see it there? You know, you could draw a little explosion, like clouds of smoke, rocket hits ground, whatever. But that's where it hit the ground. I would check your Y-min in your window. Oh, yours is broken, yes. So you just have to adjust your scale. Do you see how it goes from 0 to 10 by 10s? Well, it has a tick mark at 10, but none in between. So you can just change that to 1. Okay. Hey, Ben, what do you think? How long did it take for the rocket to hit the ground? Do you see that the path that the rocket takes? Can you see that? Like, rocket starts here, and we launch it, and it goes up, 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 hits a max. So it starts here, flies through the air, up, 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 up. That's its highest height, right? And then what happens, Ben? It starts to go down, right? And it hits the ground right there. There you go. Do you see how that worked out? That didn't come from me, that came from you. Good. So, yeah, 8 seconds is what we're looking at there. Now, honestly, you have to support this response, not just with a picture, but with some good old algebra. So we're going to go ahead and take the same approach that we did in the previous problem. I'm not going to do the quadratic formula this time because these numbers, I know that they factor. So I'm going to show you how you can also factor a little bit. So I'm going to go ahead and in this equation, if I'm looking for the time in which my rocket took to hit the ground, you want to let your height be 0. So I'm letting h of t equal 0 because that's the height at the ground. You could do the quadratic formula on that. But I see that 16 and 128 have a common factor. I'm going to go ahead and use my GCF method. Take out a negative 16t, and what's left over is t minus 8. So when you factor your method, you got to get one side equal to 0. Always try your GCF method. It worked this time. So I took out my GCF. Now I use my zero product property. I have two things multiplied together to equal 0. That means one of those things or both must actually be 0. So I set negative 16t equal to 0. And then I also have to set t minus 8 equal to 0. Divide both sides by negative 16. Oh yeah, t equals 0. That's one of the places where the graph crossed the axis. See that right there? So the algebra confirms what our graph finds. Add 8 to both sides. Oh yeah, we just found what Ben found. Took the rocket 8 seconds to complete its path until it hit the ground. That's nice. Now in part B, it's a little bit different. This time around, we're supposed to figure out how many seconds the rocket will be 112 feet above the ground. So this time, they're saying, hey, let your height, or let h of t, that's fancy talk for height, equal 112. So we take our equation and we let h of t equal 112. Once again, I know that 16, 128, and 112 all have a common factor. So I'm going to go ahead and factor this problem. In order to use the factoring method for solving a quadratic, you must get one side equal to 0. So presently, I'm subtracting 112 from both sides. Now what I'm going to go ahead and do is take out that negative 16. And then that little t squared minus 8t plus 1, you could use AC grouping, but I also know that that is pretty easy to factor because I'm looking for factors of positive 7 that make negative 8. Factors of positive 7 that make negative 8. Not bad. That's just negative 7 and negative 1. Using my zero product property, I now have to set those parentheses equal to 0. So I know from that t has to be 7 and 1. Look at how cool this is. So at time equals 1, I'm at 112 feet. And on the graph, based on how I scaled it, that makes sense. And at 7 seconds, it has to come back down. It's also going to hit 112 feet. So that's kind of cool. Those points are also points on our curve. So it hits 112 feet at 2 times. There's 2 answers to this problem. At 1 second and at 7 seconds. For part C, we're going to use our eyeballs. Parabolas are always symmetric. There's always a line of symmetry that runs right down the middle. It says, how long will the rocket take to reach its maximum height? So, right there, right? The maximum height of our graph. I have to find the time that corresponds to that. Ooh, we'll finish this one tomorrow, perhaps. You folks start teaching tomorrow. Please keep in mind, completing the square assignment should be in my bin up here. Those should be turned in. You have book work tonight. Some of you who weren't here yesterday have 2 book assignments to take a look at for tonight.